In section 3.2, we look at polynomial functions and their graphs. So first, what is a polynomial function? So we let n be a non-negative integer, and we let a sub n down to a sub 0 be real numbers, where a sub n is not equal to 0. And so the function will look something of the sort f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down until a sub 2 x squared plus a sub 1 x plus a sub 0. That's a polynomial function of degree n. The number a sub n is the coefficient of the variable to the highest power. We call this the leading coefficient. Polynomial functions of degree 2 or higher have graphs that are smooth and continuous. So by smooth, we mean that the graphs contain only rounded curves with no sharp corners. By continuous, we mean that the graph have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. And so if we look below, we can see some graphs of polynomial functions. On the left-hand side, you can see that we have smoothly rounded corners, and I can draw this shape without lifting my pencil. For the graphs that are not polynomial functions, we have discontinuity in the first graph, so I'd have to lift my pencil to draw that one. And then I have sharp corners, so they come to a point. So they're not smooth. Let's go ahead and talk about the end behavior of polynomial functions. And so the behavior of the graph of a function to the far left or the far right is called its end behavior. The sign of the leading coefficient a sub n and the degree n of the polynomial function reveal its end behavior. So if n is odd, we have two different cases. If the leading coefficient is positive, then the graph falls to the left and rises to the right. And so what that means is that it falls to the left and rises to the right. If the leading coefficient is negative, while n is odd, then the graph rises to the left and falls to the right. And so I like to think when n is odd, our arrows go in opposite directions. Now when n is even, if the leading coefficient is positive, then the graph rises to the left and rises to the right. So that means it rises to the left and it rises to the right. If the leading coefficient is negative, then the graph falls to the left and falls to the right. So when n is even, the arrows point the same direction. Now let's just dig into this a little bit more. So going back to when n is odd, when the leading coefficient is positive, I try to think of positive slope. Positive slope rises from left to right. When the leading coefficient is negative, think of negative slope. it rises to the left and falls to the right. When n is even and they're going in the same direction, when it's positive, then the arrows are facing up. And when it's negative, the arrows are facing down. Those are just some kind of hints to try to help you memorize what the end behavior looks like. So for example number 1, we're going to use this test to determine the end behavior of the graph of x cubed plus 3x squared minus x minus 3. And so the only thing we care about in this function is x cubed. And so the degree of my function, which we usually denote as n, is 3, which is odd. So that means that the arrows are going to be going in opposite directions. The leading coefficient which we write as a sub n, is 1. And so that's positive. So think of positive slope. So our arrows are going in opposite directions, and think of positive slope. So that means it's going to fall to the left, and it's going to rise to the right. So it falls left, rises right. Go ahead and pause the video and try the second one. And so for the second one, it looks like we might have to multiply this whole thing out to determine the degree, but we don't have to. And so looking at this, each piece of this factored form, the degree of negative 4x cubed is 3. The degree of x minus 1 is 2. And the degree of x plus 5 is 1. We're just looking at the powers that are associated with them. And so I can find the degree of the entire thing by adding these together. And so 3 plus 2 plus 1 gives me a degree of 6. Which is even. And that tells me that my arrows are going to go in the same direction. Now I want to look at the leading coefficient. Well, the leading coefficient is just the number that's present up front. It's that negative 4. And so because that's negative, that means that my arrows are going to be pointing down. Falls to the left and it falls to the right. Now let's go ahead and talk about the zeros of polynomial functions. So if f is a polynomial function, then the values of x for which f of x is equal to 0 are called zeros of f. These values of x are the roots or the solutions of the polynomial f of x equals 0. So zeros, roots, or solutions are the exact same thing. When we look at them on a graph, they appear as the x-intercept. And so we want to find all the zeros of f of x equals x cubed plus 3x squared minus x minus 3. So we need to set this equal to 0. X cubed plus 3x squared minus x minus 3 equals 0. So because there are 4 terms, we are going to factor this by grouping. And so we want to split this down the middle. What do the two first terms have in common? Between x cubed and 3x squared, we can pull an x squared out, and I'm left with x plus 3. Now for factoring by grouping to work, this x plus 3 needs to appear on the other side. And I need to figure out what goes in the spot up front. So if I have negative x minus 3, what do I need to put in front of x plus 3 to get to that? I would need to put a negative 1. And you can always double check yourself by distributing the number into the x plus 3 to make sure you get negative x minus 3. So now that that's done, on both sides of the purple line, we have an x plus 3, and so we can factor that out. And then what I have left over is whatever is in front of those parentheses, and that'll be grouped into the next parenthesis. So we have x plus 3 times x squared minus 1 equals 0. And so if you notice, x squared minus 1 is a difference of squares, and so we can break this down even further. And that will factor as x minus 1 and x plus 1. And so what we want to do is we want to set each piece equal to 0. And then we're going to solve. So we're going to subtract 3 on the first one. And we get x equals negative 3. That's going to be one of our zeros, or our root, or solution. In the second one, we want to add 1 to both sides. And so the negative 1 and 1 is going to cancel. And we get that x equals 1 as another root or solution. And in the last one, we want to subtract 1 from both sides. And again, the 1 and negative 1 are going to cancel. And our last zero or solution is going to be negative 1. Now what about the multiplicities of zeros? So we can use the results of factoring to express a polynomial as a product of factors. So for example, let's look at negative x to the fourth plus 4x cubed minus 4x squared, and that's equal to negative x squared times x minus 2 squared. Now notice that each factor occurs twice. The x occurs twice, and the x minus 2 occurs twice. So in factoring the equation for the polynomial function f, if the same factor x minus r occurs k times, but not k plus 1 times, we call r a 0 with multiplicity k. So for our example, 0 and 4 are both zeros with multiplicity of 2. And this excuse me, this should be 2. All right, so if r is a zero of even multiplicity, then the graph touches and turns around at our 0. If it has odd multiplicity, then it crosses. Regardless of whether the multiplicity of a 0 is even or odd, graphs tend to flatten out near zeros with multiplicity greater than 1. So let's go ahead and find all the zeros of f of x equals 1/2 x plus 1, 2x minus 3 squared, and give the multiplicity of each zero. State whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. So this is already factored. That's going to make our lives a lot easier. So let's go ahead and set this equal to 0. So we can find our zeros. And so we're going to have x plus 1 equals 0. And we're going to have 2x minus 3 equals 0. And we're going to solve. So let's go ahead and subtract 1 on the first one. And so we end up getting that x equals -1. Now, the power of that factor was 1. So that means x equals -1 has a multiplicity of 1. Which is odd. Let's go ahead and solve for the other one. The first thing we're going to do is we're going to add 3 to both sides. And so we have 2x equals 3. And then we want to divide both sides by 2. And so we get that x equals 3/2. Now the exponent on that parenthesis was 2. So this means this has a multiplicity of 2. Which is even. And so what this means, at x equals -1, because the multiplicity was odd, that means that it crosses. At x equals 3/2, because our multiplicity was even, it was 2, it's going to touch and turn around. So the intermediate value theorem tells us of the existence of real zeros. The figure shows that if a, f of a, lies below the x-axis, which is right over here, and b, f of b, lies above the x-axis, The smooth continuous graph of this polynomial function must cross the x-axis at some point to get to the other point. And this value is going to be a real zero for the function. To use the intermediate value theorem, in order to determine if a root exists between two values, what you want to do is plug in the x values into the function. If the resulting functions, or our y values, have differing signs, so one is positive and one is negative, then the root exists between those x values. If the signs are the same, then there may or may not be a root between those x values. So let's go ahead and show that the polynomial function x cubed minus 2x minus 5 has a real zero between 2 and 3. So what we want to do is we want to plug in 2 and plug in 3 and see what the signs give us. We don't care about the number, we just care to see if one is positive and one is negative. So plugging in f of 2, we've got 2 cubed minus 2 times 2 minus 5. Well, 2 cubed is 8, and 2 times 2 is 4. And so 8 minus 4 minus 5 is going to give me negative 1. Let's do the same thing for f of 3. We've got 3 cubed minus 2 times 3 minus 5. Well, 3 cubed is 27. 2 times 3 is 6, and then minus 5. And 27 minus 6 minus 5 gives me 16. So because we have a negative and then a positive, that means that there is a 0 between 2 and 3. And so let's kind of wrap this all up so we can learn how to graph. The last thing before graphing is we want to talk about turning points. So if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. And that's where the slope changes from positive to negative or negative to positive. It's just turning around. And so if I have something of degree 2, that means I can only have at most 1 turning point. If I have degree 4, then I can have up to 3 turning points. And so to graph a polynomial function, first you want to use the leading coefficient test to determine what the end behavior is. Then you're going to find your x-intercepts, which is your roots or your solutions, by setting it equal to 0, and then solving that equation. If there is an x-intercept, we want to see if it's going to touch and turn around or if it's going to cross. Then we want to find the y-intercept by computing f of 0. We can use symmetry, if applicable, to help draw the graph. So if I plug in negative x and I get the original function, we have y-axis symmetry. And if I plug in negative x and get the exact opposite of the original function, we have origin symmetry. Then we can use the fact that the maximum number of turning points of the graph is n minus 1, where n is the degree of the polynomial function, to determine if it was drawn correctly. So let's go ahead and graph the polynomial function x cubed plus x squared minus 4x minus 4 using the strategy. So the first thing is end behavior. And so the degree is 3, which is odd. That means they're going in opposite directions. And the leading coefficient is 1, which is positive. And so think of positive slope. That means it falls to the left and rises to the right. The second step is to find our x-intercepts and the multiplicity. And so we want to set this equal to 0 and factor it. So again, we have 4 terms. We want to factor by grouping. And so we can take an x squared out of the first piece, and we get x plus 1 left over. And remember, we have to have x plus 1 for this to work on the other side. So what needs to go up front? Well, we have negative 4x minus 4, and so we can put a negative 4 up front. So we have x plus 1, and then we've got x squared minus 4. Well, again, we have that difference of squares, if you've noticed. And so that can factor a little bit more. That's x plus 2 and x minus 2. And so our zeros are going to be x equals negative 1, negative 2, and 2. And all 3 of these have a multiplicity of 1. Which is odd. And so that means it's going to cross the x-axis. The third is going to be the y-intercept. And that's when we plug in x equals 0. So f of 0, that's 0 cubed plus 0 squared minus 4 times 0 minus 4. And that just gives me negative 4. And so we have the point 0, negative 4. The fourth thing we want to talk about is symmetry. And so we want to plug in a negative x and see what we get. So that's negative x cubed plus negative x squared minus 4 times negative x minus 4. This gives me negative x cubed plus x squared plus 4x minus 4. Now, was this the original equation? Definitely not, because we had positive x cubed and this just gave me negative x cubed. So this is not even symmetry. Which means there's no y-axis symmetry. Is this the complete opposite of the original function? Which means are the signs different than the original? So x cubed and negative x cubed, that is different, but x squared is positive in both. So because the signs don't differ for every term, then this is not odd symmetry either. And so that means there's no origin symmetry. And the last thing is the turning points. So because our degree was 3, that means we can have a max of 2 turning points. So let's put this all together on the graph. So the first thing is, let's go ahead and plot our x-intercepts first. So we had an x-intercept at -1. We had one at -2. And we have one at +2. We also have a y-intercept at 0, -4. Let's go ahead and plot that too. We don't have any symmetry we have to worry about, and so we know that between these x-intercepts that it crosses the x-axis. We know that our end behavior, this is falling to the left and rising to the right, just as an idea. And so as I'm drawing this, we're coming up to our x-intercept and we're going to cross, and we got to turn around to hit this other x-intercept. Again, we're crossing through this x-intercept. We need to hit this y-intercept. And we're going to come back up to hit this last x-intercept, which again we cross through, and we connect our end behaviors. And so this method allows you to draw a graph and give you an idea of what this function looks like.